Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's a great pleasure for me to welcome everyone here in the Smithwick Theater at Foothill College, and everyone listening to us or watching us on the web to this very special lecture in the 17th Annual Silicon Valley Astronomy Lectures. This series of non-technical lectures is designed to fill in the members of the audience and those in the web audience on the latest developments in our understanding of the universe. And we're very happy that this lecture series is co-sponsored by NASA's Ames Research Center, a major center for NASA around the country, the Venerable Astronomical Society of the Pacific, a public education organization in astronomy, the SETI, or Search for Extraterrestrial Intelligence Institute, a scientific and educational organization devoted to understanding more about life in the universe, and then the Foothill College Astronomy Program. And it's my pleasure to welcome all of you on behalf of those sponsors. Tonight's speaker is one of our favorites. She is back for a second engagement here. Dr. Lynn Kaminsky is the chair of the Physics and Astronomy Department at Sonoma State University, where she's been on the faculty for over 30 years. She's the founder and director of Sonoma State's Education and Public Outreach Group, which develops educational materials for NASA, for the National Science Foundation, and for the US Department of Education. Her research focused on black holes, the X-ray universe, and high-energy astronomy. So whenever we have something happening that's bizarre and unusual, we always call on Dr. Kaminsky to explain it to us. More recently, she's been a leader in developing exciting educational materials to help inspire students to pursue scientific careers, and she's been teaching teachers nationwide, and also scientific literacy for the general public has been very much in her radar screen, on her radar screen. Among her awards are the Wang Family Excellence Award for the California State University System and the Astronomy Education Award of the American Astronomical Society, which is perhaps the highest award that someone in astronomy education can win. So we are delighted to welcome to the Foothill College Smithwick Auditorium, Dr. Lynn Kaminsky, speaking about Spacetime Symphony, Gravitational Waves for Merging Black Holes. Dr. Kaminsky.
Well, thank you for that very kind introduction. You might wonder a little bit about this birthday cake here. We're just a little past the one-year anniversary of the birth of a new field of astronomy, gravitational wave astronomy. So I'm here tonight to tell you all about how that happened. This was the scene in February of this year at the National Press Club in Washington, D.C., and I was lucky enough to be able to be there to hear the big announcement.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Okay, so you might wonder, what are gravitational waves and why was everybody so excited about that? That was Dave Reitze. He's the director of the LIGO laboratory at Caltech, and other people in the audience included Franz Cordova, the director of the National Science Foundation, and other people from the project. So what are gravitational waves? Well, the official buzz phrase is ripples in the fabric of space-time. But what does that mean? The waves were predicted in 1915 by Einstein when he developed his theory of general relativity. And basically, when the wave travels through space-time, it stretches and squeezes the entire fabric of space-time. So here's the simple version. These are all little tiny objects in space, and as the wave passes through, you can see In one direction, it's getting squished. In the other direction, it's getting pulled apart. And then the directions alternate. More realistically, it might look something like this figure on the right, where you can see the wave traveling through space-time as the different parts of space are alternately stretched and compressed. The waves travel at the speed of light. That is a prediction that comes from Einstein. Einstein also had a very different way of looking at gravity, and you may have seen pictures like this before. This checkered fabric here is supposed to represent the fabric of space-time. This is the sun, this is the Earth. Objects that have a larger mass make a bigger curvature in the fabric of space-time. Now, what's confusing about this picture is it looks like space-time is two-dimensional. But that's because we can't actually draw a picture in 4 dimensions. In fact, on a screen, you can only draw a picture in 2 dimensions, and we try to pretend there's the 3rd dimension. So really what's happening is that for any massive body, the space-time is curving in around it from all directions, right? It's not just this one direction underneath it. This is just the only way we can really portray it simply in a 2-dimensional drawing. So picture this kind of curvature, but bending in around the object in every dimension. Now, this is a very different way of looking at gravity than Newton looked at gravity. For Newton, you had these 2 objects. There's the Earth, there's the moon. The force of gravity just worked on a line between the 2 objects. The force was transmitted instantaneously. And for those of you who like equations, this is Newton's famous equation of gravitation. The force goes down by the 1 over the distance squared. And of course, there's the apocryphal story of Newton sitting under the apple tree and the apple falling down and him looking up at the moon and realizing that the same force that has the moon orbiting the Earth is the same force that had the apple fall on the ground. But these 2 different ways of looking at gravity are really very different. So for Newton, space was flat and time was a constant. And that's really how we experience it in our everyday lives. You needed 2 masses to have gravity because it was a force between 2 masses. It acted instantaneously, and light would travel in a straight line. Now for Einstein, space and time are all mixed up. That's why we call it space-time, right? They're intertwined. But you can have gravity just with one single mass sitting there because any mass will curve space-time. And it's that curvature that we experience as the gravitational force in Newton's way of looking at things. Also, for Einstein, gravitational waves travel at the speed of light. Nothing happens instantaneously. If the sun disappeared, 8.5 minutes later, we would notice that here on Earth, right? The gravity from the sun would be gone, and it would take that light travel time for us to tell that something had disturbed the gravitational field. And light doesn't go in a straight line, but it does follow the shortest path through space-time. And if space-time is curved, that shortest path is like a geodesic curve. So the path of light rays can curve if you're traveling through space-time where you've got massive bodies. Now, black holes are the most massive and dense bodies that we know about in our universe. Of course, they're very famous for not letting light escape once the light gets too close to the black hole. That's the region that we call the event horizon or Schwarzschild radius. Because if you were traveling at the speed of light at that radius, you could just escape. But once you cross that radius, even traveling at the speed of light, you can no longer escape. So light will get sucked into a black hole, which is why we call them black. If a collapsed stellar core doesn't have enough mass to collapse all the way down to make a black hole, that's roughly 3 solar masses, 3 times the mass of our sun, then it'll make another interesting object called a neutron star. And I've spent my whole career basically studying neutron stars and black holes, but looking at them with electromagnetic waves, such as X-rays or gamma rays, the highest energy electromagnetic waves. So I was very excited when I got a chance to join the LIGO project back in 2007 to help them with their educational offerings, because I would get to study all my old friends, the neutron stars, the black holes, things that are blowing up, but with a totally different way of observing them, namely through gravitational waves. The very first black hole was named Cygnus X1. It's located in the constellation Cygnus the Swan. It was discovered by a rocket flight that had X-ray detectors on it. And it has a mass of about 16 times the mass of our sun. We could tell that because it's orbiting a normal star. Well, it's a supergiant, but it's a normal star that's making starlight like our sun makes starlight by burning fuel in its core. And the two are orbiting around each other, and we can see the black hole tugging on the supergiant visible light star, and then we can measure its mass by how much it tugs on its companion. So that was the first black hole that people really identified, and that's been commonly accepted by scientists. There was also, before LIGO, indirect evidence for gravitational waves from the work done in radio astronomy by these two gentlemen. This is Joseph Taylor and Russell Hulse, and they discovered a system of two neutron stars, so only 1.4 times the mass of our sun, orbiting each other, one of which was a pulsar. So with the pulsar, as the neutron star orbits around, it makes a pulse of light, radio light in this case, and that can be very accurately timed, the spin rate of these neutron stars. And so they discovered this system, pulsar PSR 1913 plus 16, that's where it's located in the sky. And one of them was a pulsar, so they could time the orbit of this system very accurately. Here's the years, 1975 all the way up to 2005. And what they discovered was that the orbit of these two neutron stars was shrinking as a function of time. And it was shrinking exactly at the rate predicted by Einstein's theories if the energy was being removed from the system by the emission of gravitational radiation, gravitational waves. So that was not like seeing the waves themselves, but it was evidence that gravitational waves exist. And you can't even see the error bars on these data points because they're so small, and it lies exactly on the curve that was predicted by Einstein. And so they won a Nobel Prize for discovering this binary system. And then they continued to follow it for many, many years. It's still being followed. OK, so now, hopefully, this is going to work. It doesn't look like the first video actually played, but we'll give this one a try. This is the, oh, good, it's working. This is what it would look like if you were near two black holes that were orbiting around each other, and they were about to merge. And they're going to merge here in a second. As you can see, the black holes having a lot of gravity bend all the light around them so that this ring that you're seeing is actually the light from the stars behind them that's being lensed around and ending up in front of them. OK, now they're starting to merge. Now they make one big black hole, and it sort of wiggles like a bowl of Jell-O for a little while, and then it calms down. So if you could get close enough to two black holes and you could see them in visible light with your eyes, that's what it would look like. Of course, if you were that close, you'd probably not be alive, but that's another matter entirely. OK, so now here's the same situation with our two-dimensional diagram showing the two black holes orbiting around each other. Now, these are all the gravitational waves that are coming out as they're orbiting each other. And as they get closer and closer, the waves get closer and closer together, and then they merge, and then you get a big burst of waves, and it just travels outward at the speed of light. Now, these calculations, the first one and this one, these are done by a group using all of the equations of Einstein's general relativity theory. Okay, supercomputers, hundreds of hours of supercomputer time, everything is calculated exactly. These are not drawings or animations done by artists. These are actually numerical calculations. OK, so now what about LIGO? So what is LIGO? LIGO stands for Laser Interferometer Gravitational Wave Observatory. L-I-G-O, they'd skip the W. Okay, so we're going to use lasers as rulers to measure the length of the two arms of the interferometer. You'll see this play in a second. And when the gravitational wave comes through, it's going to stretch one arm while it compresses the arm that's 90 degrees away, that's at a right angle. And that's going to alternate as the wave passes through. And by measuring the difference in the length of the arms, we can actually directly measure the waves. So now we'll see how this works in the simple version. So there goes the laser. It splits at the beam splitter. It goes down this arm. It goes down this arm. Here comes the wave. See, the arms are changing length. And this is the screen where you read out the wave pattern. So there's a wave. We're just going to travel down one arm now and see it bounce back. Normally, if there's no wave going by, these two waves cancel each other out exactly. So you don't get any signal on this detector here. But once the lengths of the arms change because the wave passes by, the combination wave that is the sum of these two waves can get brighter or dimmer as the wave passes by, and so you can see that. And we read that signal out to see the wave passing by. So as the waves add up, you get a brighter signal. As the waves cancel each other, it goes to dark again. But that's not really what the NSF spent $1 billion building. That's just the cartoon version. So this is a project that goes back 40 years. Now, okay, here's the more realistic version. I made this video with a wonderful animator over the sun. This is Hanford, and this is a fly-in to the control house where the beam splitter is. There's the two arms. Now you get to see what it really looks like. This is from the CAD drawings. Okay, each one of these arms is 4 kilometers long. The longer the arm, the better chance you have of measuring things. All of the laser beam stuff is inside these big things called hams, which isolate it from any seismic noise coming by from the earth, a truck driving by, someone cutting a tree down in the forest. All of those things set off the detectors, and you have to be able to correct for that. So the laser beam comes through. This is a system that boosts the power and cleans up the signal. Now here we go to the beam splitter. So this is the thing that was on the other thing. It's going to split and go down the 2 4 kilometer long arms. We'll fly into the beam splitter. You can see what it really looks like. Each one of these things is a big seismic isolation mount. Okay, so we go down the arm, there's the beam. It actually goes back and forth about 450 times and builds up in power between the mirror at the end and this beam splitter mirror. Now we're going to fly down one of the legs so you can see what the mirror looks like at the very end. This mirror is actually suspended on 4 sets of coupled pendulums, so that anything that wiggles the top, the big mirror at the bottom, which weighs 40 kilograms, will hold still. And it's suspended by millimeter-wide glass fibers, a 40-kilogram mirror, these tiny, skinny fibers. Now they come back together again at the beam splitter, go into another set of electronics that cleans up everything, boosts the signal some more. Eventually we get to the output mode cleaner, which is another thing that cleans up the signal some more. Each one of these is in these big seismic isolation mounts called the hams. And then somehow it didn't show the end of it. Oh, well, you didn't get to see the, oh, okay, it's doing it now. So it's, of course, greatly exaggerated how much this thing is stretching and shrinking. And then you'll see we draw the signal up here that was actually a signal that was seen. Okay, so there it goes. There's the real signal. Okay, but this is greatly exaggerated. There are 2 of these observatories. We decided to model the one in Hanford, Washington State, and the other one is in Livingston, Louisiana. And you need to have 2 of them, because if you saw a signal in just one of them, you wouldn't necessarily believe it. right? It could be a truck driving by. It could be something that you couldn't explain. So you need to see the same signal in both of the interferometers. And it's a little trickier than that because one of them is oriented one way and the other one's oriented the other way. There's Hanford, there's Livingston. 10 milliseconds, if the wave is going right across the surface of the Earth, it would take 10 milliseconds for the signal to get from one to the other. But also, it's inverted, okay? Because the interferometers are facing opposite each other, the signal from one is upside down from the other one. So if this one's going up, this one's going down. So these are additional things that we can use to check to see if it's really a true signal. So, okay, what did we observe? So the very first gravitational waves were observed by LIGO at the end of the engineering run that led to the beginning of the first science run in September 14th, 2015. So we call it GW150914. Okay, so that's where the name came from. That's why I said we're a little past the first year anniversary. So here are the data from Livingston. This entire data is only about 0.25 seconds long, and you can see the wave pattern. And here are the data from Hanford, and they've already been flipped upside down, and they've already been shifted by, it turns out, 7 milliseconds. So then what you do is you take Einstein's predictions for what would happen if two black holes merged. You do lots of computer runs to simulate all the different sizes and shapes of black holes that you could imagine, orientation, spin, and then you fit the two data sets. Those are the model fitting, the little curves that just got laid on there. And this first burst, this first gravitational wave, was so bright that people could see it in the very lightly processed data. And both detectors gave the exact same model results. So that was amazing because we didn't even know that there were systems with two black holes orbiting each other that were even out there. Okay, that's never been seen in electromagnetic radiation. So what we're measuring is this thing called strain. It's the change in the length of an arm divided by the length of the arm of 4 kilometers. The maximum strain that we measured was 10 to the minus 21. So if you do a little math here, you can see that that meant that the length of the arm only changed by 4 times 10 to the minus 18 meters. That's 4 1,000ths smaller than a proton. So how do you measure something that's smaller than an elementary particle? Well, you have this big mirror, and you're averaging over lots and lots of atoms on the mirror. And so you can do that. But it's like being able to measure the width of a human hair over a baseline that's the distance to Proxima Centauri, the nearest star, 4 light years away. I mean, it's an incredible feat of measuring to be able to do that. Okay, so now why do we call this Spacetime Symphony? Well, we use the analogy that when we're looking at light, all the different kinds of light, we're seeing the universe with our eyes, even if it's X-rays, which you can't see with your eyes, but we still think of seeing the universe. It turns out that the gravitational waves that we're detecting, and you can see those wiggles, they are very close to the band of, in hertz, cycles per second, that we hear. So we find it convenient to translate this wave signal into an audible sound. So the analogy is we're now hearing the universe. We're listening to the symphony of the universe with these gravitational waves. Whereas when we look with electromagnetic waves, visible light, X-rays, we're seeing the universe. So what do these things sound like? So here are the first, we call them chirps, because, and I'm going to play this a couple times, because it starts at a lower frequency and it goes to a higher frequency. So it's like, whoop, whoop. That's like a chirp noise. Okay, so hopefully you'll be able to hear this. Now we shift it up so you can hear it better. Whoop. So could you hear that? Could you whoop at the end? It's easier if we shift it up by about 400 hertz because it's closer to the hearing band. It sounds more like a thump when you just hear the first signal, but it's still cool to listen to. I'll do it again. I love listening to this. And all that background noise is stuff that has to be subtracted in order to do the modeling and to fit the signal. And so you see the waveform down here. And as these little waves get closer and closer together, that means the frequency increases. And then the color is telling you, so here's frequency. The color is telling you how bright it's getting, how loud it's getting. Okay, so we're looking at two different things. And if you remember the cartoon of the two black holes merging, the simulation, with the waves coming out, right, as the black holes got closer and closer together, they spiraled faster and faster, so they made waves that were higher frequency, and the strongest waves came from right when they merged. And then it just sort of settles down afterwards, sort of relaxes into its final state. So those are the very first gravitational waves that were ever seen. And of course, we got a lot of fun press. like this cartoon with the birds. Was that you I heard just now, or was it two black holes colliding, right? Because we call them chirps. That was from the New Yorker. I thought that was a cute one. But it was tremendous amounts of popular press when we had the press conference in February. And in my group, we worked on trying to explain this to the public, doing the educational piece. We've done an educator's guide that explains this for teachers and has some classroom activities that you can use. And my wonderful artist, Aurora Simonet, did this image based on the numerical simulations of what it looks like for black holes to merge. Here they are spiraling together. Here they are at the point of merger. Here's the ring down right afterwards as the thing settles down. These are the real waveforms from Hanford and Livingston. And this was the astronomy picture of the day for the day of the press conference in February 11th, 2016. So we were very happy with that. Okay, so what did we learn about the black holes? Okay, so one first is the first gravitational waves ever seen. Another important first is it's the first time we ever knew that there would be two black holes in one system that would merge. Remember the work that Hulse-Taylor did was two neutron stars, not two black holes. We know of many other situations where we think we've seen neutron stars merging. Mostly they make short gamma ray bursts, which is something that I study with one of my NASA satellites. But there is no evidence for any of these stellar mass black holes to be in binary pairs. For one thing, they're not expected to have a lot of matter around them, and so we don't expect to see any electromagnetic radiation, any kind of light coming out of them at all. They should have sucked in all of their surrounding gas. At least that's what some theorists think. So what you do is you fit those waveforms with the models, and then you see what it tells you about the black holes, and this is what we learned. The black hole mass for the heavier one was about 36 times the mass of our sun. The lighter one was 29. When they merged, the final black hole was 62, and if you add those up, you'll discover that that means three solar masses worth of energy went out in the gravitational wave. At the moment that that merger happened, the amount of energy coming out in that gravitational wave was brighter than all of the stars in the universe, in all of the galaxies, just from this one merger event. It's at a distance of about 410 megaparsecs, so about 1.3 billion light years. And that's the redshift, for those of you who like redshift. And the final spin of the final black hole was about 2/3 of the maximum possible spin that a black hole can have. That isn't actually a number, it's just a parameter that you can get from the model. But it means it was spinning very rapidly. And these are the error contours that you can see how well we know those things. So aside from the fact that the two black holes were merging, and we've never even seen two black holes in a binary before, each one of these black holes by itself was about twice the mass of the heaviest black hole that we knew about from the Cygnus X1 kind of black holes, where they're orbiting around a regular star. All of the black holes that we've studied with X-rays and gamma rays that are stellar mass black holes are about 15, maybe 20 solar masses. These guys at 36 and 30 were, heavyweights. We've never even seen a single black hole that's that size in any of our electromagnetic radiation measurements. Now, of course, we see millions and billions of solar mass black holes in the centers of galaxies, but I'm not talking about those kind. That will be your January lecture. I'm talking about the ones that were made from stars. Okay, so was there any electromagnetic radiation that accompanied this? Could we see any gamma ray bursts? Well, it's hard to know where to look because LIGO can't do a very good job of positioning things, and it was about a 600 square degree position. But then about a half a second later, the Fermi Gamma Ray Burst Monitor saw a weak gamma ray burst. And it was roughly consistent in position on the sky, but it's really hard to say whether it was really associated with it. First of all, nobody believed that there should be any matter, and you would need matter to make the gamma rays, right? Because the black holes should have sucked in everything. But if there was some matter around, it's possible that it was associated. And we really need to get a much bigger collection of these events before we'll be able to see whether there's any electromagnetic counterparts. But it's an intriguing finding. And so we'll stay tuned for future results. Okay, so then is that all? No, we saw another one. So we call this one the Boxing Day event because Boxing Day is the day after Christmas, apparently, in the UK. And a bunch of the people, the LIGO Scientific Collaboration, of which I am a member, has 1,000 people in it from 15 different countries. So the people from Britain named this one the Boxing Day event. So this one is called GW 151226. And this one is not as strong as that very first one that we saw. The black holes were not as massive. We had a 14 solar mass black hole plus an 8 solar mass black hole that made a 21 solar mass black hole. Is about the same distance away. It was about a factor of 3 less intense. And if you notice, 14 plus 8 is 22, 21 solar mass black hole afterwards. So only 1 solar mass of energy came out in the gravitational wave. Right? The first one had 3 solar masses of energy coming out in the gravitational wave. So it makes sense that it was about 1/3 as strong. And here's the same kind of diagram. We call this an omega scan, where you can see how bright it was as a function of time. But what was really neat about this one is it actually lasted longer. So now I'm going to play a little comparison of the chirps from the first burst to the second burst. So this is the unmodified sound. Okay, that's the new burst. Here's the original burst. Now we'll shift it up so you can hear it better. Okay, so now I'll talk over this one. I'll play it again. So what you see from the new burst, which this one is you can see it for a lot longer before the merger event, right? So here's the new second burst. Here's the first burst. It's much shorter. It's brighter, but it's shorter. So we saw something like 30 waves before the merger event in this second burst, the Boxing Day event. And that might be a little surprising because it was a fainter signal overall. But basically what happened is because the black holes were smaller, they were already orbiting faster before they merged. And the speed at which they were orbiting translated into frequencies that LIGO was more sensitive to, whereas the bigger black holes before they merged were a little slower, and it was not in this favorable part of LIGO's band. So we only got a couple of spirals before they merged, whereas we got like 30 spirals before the Boxing Day event black holes merged. So it was still a very significant event. And we had another press conference about that one. It was at June, AAS meeting. That was exciting. So here you can see this a little better. These are on the same scale. Okay, so here's the first event, here's the second event. You see how this is a much higher frequency before the merger, right? This is a lower frequency before the merger. And really, we only saw this much of this one, the last 0.2 seconds. Whereas for this one, we saw back about that far. And unfortunately, LIGO doesn't do a very good job of figuring out where these things are coming from on the sky. All of the positional information comes from that 7 millisecond delay between the first detector seeing it and the second detector seeing it. It's like you had 2 microphones and you had all of space and you were listening to the 2 microphone signals to figure out what direction the thing came from. Well, you sort of get a big circle, right? So the first event, because it was stronger, it's about 600 square degrees. The second event, we could only limit it to about 850 square degrees on the sky. And so that doesn't help you very much if you're trying to figure out where the black holes really were. But this was just LIGO's first observing run. This is where we started. This was the first event right at the beginning of the run. Here is the second event right sort of near the end of the run. The run lasted about 4 months. There was another really good event that wasn't quite statistically significant enough to claim as a detection. We call that one LVT 151012. We don't call it GW because we can't really prove it was a gravitational wave, but it sure seemed like one. It was also about 20 solar mass black hole that was formed. So people say, well, how many of these do you think you'll hear? And I say, well, about 1 a month, based on our small sample of statistics. And LIGO being this incredibly complicated instrument, we turned it off in January. It's been getting tweaked up all summer, all spring, summer, fall. It's just about to go back into observing mode now. In fact, I think they're in the engineering run right now. This was to start on Halloween, so here we are 2 days later. And probably in another week or two, we'll be in an official science run once both interferometers are working again and have achieved stable working conditions we call lock. And so we should be seeing more things very, very soon. But we still won't know where they're coming from, because with just the 2 observatories, we can't really do a very good job with the positions. And so now everybody around the world is trying to build these things. The people in Italy at Virgo, and they're part of our collaboration, are just about to bring their improved interferometer back online. Theirs has an arm length of 3 kilometers. There's GEO 600, which is only 600 meters, so it's not very sensitive. It's in Germany. But it was looking in case a supernova went off in our galaxy while both Virgo and LIGO, both LIGOs, were down for these upgrades, which produced the sensitivity that led to the detections. The Japanese are building an underground interferometer that's cryogenically cooled called Kagra. That'll probably come online around 2020, maybe. And we just signed an agreement and got permission to take the extra set of hardware that we made for LIGO, because Hanford used to have a 2-kilometer interferometer as well. But instead of putting another one in the same place on the Earth, we have made a deal with the folks in India, and they are going to be building all of the vacuum tubes and all of the electronics, and they're going to get the LIGO detectors and the LIGO mirrors. And that will probably come online in maybe 2024. We're hoping. They're doing site selection in India right now. Of course, we would have loved to have had one in Australia, because then we would have really the southern hemisphere, but unfortunately the Australians didn't have the money to build everything. They're building radio telescopes and other things, and so that was their priority, because that would have, you know, ideally you want it as far away from these guys as possible, and as far south as possible would be good as well. But India, I think, will be good once it's finally working. But that's not really the end of the story, because just like light has all these different frequencies, from radio waves at the low end to gamma rays at the high end, gravitational waves are expected to have a whole spectrum of frequencies as well. And what LIGO saw was really at the higher end of the gravitational wave frequency spectrum, with periods, you know, we saw all those waves in just a couple tenths of a second, right? So what people are doing, and this is actually, this one is funded. So this one is to put basically LIGO in space by shooting laser beams between 3 satellites. And so the concept for that is LISA, Laser Interferometer Space Array, or antenna. And they've just flown the Europeans have just flown a Pathfinder mission for LISA. That was very successful. It proved that they could hold a mass in free fall and know where it was very accurately, because you need the satellites to fly information, you need the laser beams to be stable. But the big advantage of space is you can have 5 million kilometers between each satellite, and there's no seismic noise, and there's no trucks driving by, and there's no trees getting cut down, and things like that. So it should be a great environment to do gravitational wave astronomy for longer wavelength waves, minutes to hours. If you want to look at even slower waves, things that would take years to decades for one wave, what is going on right now are called pulsar timing arrays. So you've got a network of really big radio telescopes on the ground, and you've got, say, 35 right now, hopefully someday 50 or 70, of these neutron star pulsars that are spinning around at millisecond periods, very, very stable clocks, and you know exactly when all the pulsars are supposed to arrive from all of these pulsars all over the whole sky. And when the wave goes by, it should subtly change, because it's changing the length of space-time in between all these pulsars. It should subtly change the arrival time of the pulses. And so by looking very carefully at all of these millisecond pulsars all over the sky with the world's best radio telescopes, it's called a pulsar timing array, they should be able to detect a much longer one of these waves. And then last but not least, there would be an imprint on the cosmic microwave background of gravitational waves that should have polarized the microwave light in the cosmic microwave background. Now, this was claimed maybe a year or so ago by the BICEP group, and you might have seen the press about that. It made a big splash. Oh, they found evidence for gravitational waves from the Big Bang. And then, unfortunately, it turned out to just be scattering by dust, and they had to retract it. And so we, the LIGO team, were very concerned, because we did not want to have the same kind of situation with the press and with our scientific announcements. So we knew about the wave. It took 6 months to go through all of the internal vetting processes on the team before we decided to have, and of course the paper got accepted before we had the press conference that announced the big discovery, because really extraordinary claims, as you know, require extraordinary evidence, and we just wanted to make sure. And people were so surprised. I mean, we really thought the first thing we'd see would be neutron star merger, and it would be much fainter, and we'd have to convince ourselves that the signal is real. And instead came in this huge, exciting blast from these 2 black holes that were bigger than anybody even knew existed. And that was the first thing that we saw. So it was quite an amazing thing to be able to see something without having to depend on computer models to convince you that it was real. And it made everybody feel much more confident in what they were predicting. And so we have started this new era of gravitational wave astronomy. We will be able to hear the universe and not just see the universe. We call this multi-messenger astronomy. Every time we have a different kind of detector or a different kind of way of looking at the universe, we find unexpected things, things that we could have never even dreamed of, although the theorists can dream of everything if you give them enough time. We have satellites that look at light. We have radio telescopes on the ground. We have air shower arrays to look at cosmic rays coming down, neutrinos, which are other very energetic particles, right? So this is multi-messenger astronomy. Every different kind of thing that comes to us from the cosmos gives us a clue to a different piece of our universe that we get to explore. So let's raise an in-spiral toast to the beginning of gravitational wave astronomy, and I want you to all try this at home. Okay, well, thank you very much. Done by some of our Scottish colleagues who were out celebrating. And here's some resources. The main LIGO website, if you want to see where all these movies and graphics came from. This is my own website where I have materials like the Educator's Guide, and I did courses for the past 2 summers to teach lower division physics instructors all about this so they could teach their students, and those materials are all on there for free. And if you want to listen to some really cool sound files, I would encourage you to check out sonsofspacetime.org. And now I'll be happy to take questions if people want to line up. So. Well, except that I think we're going to have a little pause here.
No, I just want to say thank you for making us all vibrate with excitement. And we want to, let's thank Dr. Kaminsky again.
2 short questions. Will there be Doppler shift effects for the waves that you see coming in if the objects are moving away or towards us in general, the system? And then second, what would cause like the decade-long frequencies of gravity waves? What phenomena might?
Okay, so the first question, will there be Doppler shifts? Well, so a Doppler shift depends on the wave traveling through a medium, but in this case, the waves are the medium. They're distorting the medium, which is space-time, as they go through them, so no. Okay. And the second question was, what would cause a decade-long wave? And it would be a much bigger system merging. So we have seen a couple of images from Chandra of 2 massive black holes in the center of a galaxy, and if those were to ever merge, that would take a long time. So you might expect to see a much slower wave signal from that kind of a merger of something that is much heavier.
Okay, thank you.
2 very brief questions. One, if you were standing reasonably close to these 2 black holes colliding, and you're like right where the gravitational wave is at a substantial amplitude, is there anything in human sense mechanisms you'd be able to sense it or know that it just went by?
Okay, so standing near merging black holes is a theoretical problem that can't actually be done in reality.
I understand that.
So, okay, so let's start with you're outside the event horizon, so that you can actually communicate what you've just experienced. And you know, you're about, let's say you're 1 AU away, so you're as far from the merger as the Earth is from the sun. Mm-hmm. Okay, then what would happen is it would break your eardrums, basically. So it would be something that you could actually physically experience, and it wouldn't kill you if you were about 1 AU away. Other than that, you'll be stretched and squeezed if you're too close, and you all know what happens as you go to fall into a black hole. You become spaghettified, right? So you'd have to be outside the spaghettification zone to survive it. So about 1 AU is safe for one of these mergers.
Okay. I understand that in the vicinity of a black hole, time slows down and basically reaches the point where it stands still. What does that do to the rate at which these 2 black holes are falling into each other? Okay,
well, that time slows down thing, that's for like somebody watching someone else falling in. For the person that's falling in, time doesn't change at all.
But
Okay.
for the outsider, yeah.
So if you're the person that's there, you know, you still see the wave go by, because you're in the space-time with the black hole. If you have an external observer watching someone else fall into a black hole, what they see is that person sort of gets stuck on the event horizon and get redder and like become frozen. Okay, next question over here.
I read something that said that gravity waves leave a permanent deformation of space-time after they go through it.
Okay, do gravitational waves permanently deform space-time? No, they travel through space-time and they just deform it locally as they move. Maybe what you're thinking about is the permanent imprint on the polarization of the cosmic microwave background. That is a permanent imprint that was left by the gravitational waves that left from the Big Bang. But these gravitational waves that I'm talking about, they're caused by a singular event. They just travel through space-time.
Two questions. First one, when the gravity waves get to the end of the universe, do they bounce back? And the second one, really, and the second one is, as they're going through the universe, they're essentially stretching and compressing things. Is that where the energy dissipates? And could that be something people have realized, you know, there's this energy here, where is it coming from? You know, because we're talking about a lot of energy when that happens.
It is a huge amount of energy that's traveling through the universe, and it is affecting the space-time that it's traveling through. But by the time these waves reach the Earth, as you can see, they only change the length of this arm of this interferometer by such a tiny amount that you could never really notice it unless you had built $1 billion interferometer.
But the whole Earth itself would be squeezed a little bit. And
the whole Earth
heat
itself would in
come off of
fact be squeezed by 4 times 10 to the minus 18 meters. But you would never notice that.
But the whole Earth does. In other words, that would be a lot of energy absorbed in the Earth. Wouldn't that heat up the Earth a little bit?
It doesn't get absorbed, it passes through. Okay, so the gravitational waves affect the space-time, but it's not like light energy that gets absorbed by matter and then gets re-radiated. People have actually looked into whether you could lens gravitational waves and see them being lensed like you can lens light waves. And there are some calculations that shows that you can do that, but we're way far away from being able to detect those kind of effects. And since we don't know if there's an end of the universe, there's nothing that we know of that they can bounce off of.
It seems to me that you, in a very satisfactory way, detected what was predicted by Einstein. Was there anything that you found that was surprising that you did not expect?
We did not see, well, the big surprise was that the black holes weighed so much because we did not know about black holes that were in that mass range. So that was probably the biggest surprise, and it's more like an astronomical surprise as opposed to a general relativistic surprise. Every test, every model, every measurement that we've made, absolutely consistent with the general theory of relativity. So were we surprised that Einstein was right again? Nope.
But apart from the size of the black holes, you didn't discover anything new that you hadn't expected at all.
Well, that was enough new. We were happy with that. You know, more fun awaits as the detectors get more sensitive, right? So every time they turn them off and tweak them up, we try to get closer to the design sensitivity. So there may still be some surprises in store when we turn on the next time. Every time you look in a new wavelength band, you always see something you didn't expect. So that's one of the best things about doing astronomy.
Could you make the connection between the gravity waves and the polarization of the cosmic microwave background radiation maybe a little more clear and
Probably
and
not.
what and okay, fair enough.
I'll give it a try. I'll give it a try, but it may not come out terribly clear.
My interest in it is what can be learned earlier than 380,000 years after Big Bang about
right, and
the
so
Big
that
Bang.
so that is the hope, of course, right? Is if you can see this imprint in this polarization structure of the cosmic microwave background light, then you can learn something about the size of the waves, the scale of the waves, and that will give you information about what happened before the cosmic microwave background was formed at 380,000 years. So basically, the waves, by stretching and compressing the space-time, end up making these swirly patterns in the polarization. But it's fairly complicated, so I can direct you to a paper where you could read about it.
Thanks anyhow.
The width of a proton is pretty small. What frequency of light is emitted by the LIGO lasers?
Oh, these lasers are 1064 nanometers, so they're red lasers.
Thanks.
Hi, I had a question in my physics class which didn't really get answered, and that was, what causes gravity?
Okay, so that depends on whose theory you're using, right? So when you're in a college physics class, you learn that it's a force between two masses. But that's an empirical statement, right? Because you can measure that force, and it's 9.8 meters per second squared, here on Earth. In Einstein's view, mass causes gravity because mass curves space-time. And gravity is actually just the curvature in the space-time. So when you had the two black holes, they each had curved space-time around them. Then they merged. They had a different amount of curved space-time around them. The curvature holds energy. I mean, think about like a rubber band or a rubber sheet. The more you squeeze it or twist it, the more wound it gets. And so those 3 solar masses of energy that went out in the wave, that was basically just sort of a release of some of that curvature, some of that stored energy. Because the curvature around the final 61 solar mass black hole was not as much total curvature as they each individually had before they merged. So you can choose to think of gravity as either curvature of space-time or a force between two objects, whichever is easier for you to calculate in your physics homework. I bet it's Newton's version.
So you got 2 rotating objects and they give off a chirp, and so you're looking for that pattern. What other patterns are you looking for? What other type of phenomenon do you think you could see?
Okay, so what else are we looking for between 2 things that are orbiting each other?
Well, are you looking for other things besides just orbiting? I mean.
Okay, so these binary coalescent signals are the easiest thing to model because you can exactly calculate the waveform of the signal from Einstein's equations. And then what you do is this process is called match filtering. You slide the pattern that you've just calculated past your data and see if it fits, where it fits the best, and then you change the masses and you do it again. And we have hundreds of these models. If you're going to look for gravitational waves from some other kind of event that's not a compact binary merger, so say it's a star blowing up asymmetrically, or some other kind of cataclysmic event like that, you don't have any a priori knowledge of what that waveform should look like. And so you have to use very different analysis techniques. You look for correlated excess noise between the 2 interferometers and try to associate that, hopefully, with something electromagnetic like a supernova that just went off nearby. Those searches are much harder because you have no advanced knowledge of what the waveform should look like. So, that's next on the list is supernovae. Then there could just be stochastic noise left over from the background radiation, even harder to find. So the main groups within the LIGO scientific collaboration are the compact binary coalescence group. The continuous wave group form a pulsar that's spinning around that has a bump on it. Okay, so if you have a perfectly symmetric spherical object that's spinning, you will never see gravitational waves. Gravitational waves, for those of you who are mathematically inclined, come from time-varying quadrupole moments. So you have to have something like an orbit that's not spherically symmetric because it has a preferred direction. So it's got a time-varying quadrupole moment, or a star that blows up off-center, or a star that's spinning around with a bump on it. That is, or a star that's not spherically symmetric, like a squashed star that's, like a little bit of an oblate spheroid. Any one of those things can make gravitational waves. The pulsars, we know what their frequencies are because they're making pulses. So lots of people are looking for those signals. Those are waves that are easy to predict. The stuff that blows up, that's the hardest thing to look for that we're going to be looking for. But there's a whole group within LIGO that specializes in looking for the excess noise kind of signals. Probably later. Many years from now, they'll find that one.
Yeah, I have a hard time visualizing how these two black holes met each other. I mean, were they going in a straight line and happened to?
That's a really good question, right? How did the two black holes get into the binary system in the first place? That is a really good question, and it's related to the question of how does one black hole get into a binary system with a star, right? So if you're going to make the black hole out of a star that blew up, and you still had a core left that still weighed 30 times the mass of our sun, it had to be like a 100 solar mass star to start with, right? Then it went supernova, the outer layers flew off, the inner core collapsed, and it stayed together and became this 30 solar mass black hole. But then you have to have another one right next to it do the same thing, and not have enough energy while each one is going supernova to disrupt the binary. That's the tricky part. So most of the time when people do these calculations to make these systems, they do them inside of a cluster of stars, like a globular cluster or something else where there's a whole bunch of stars already close together. And maybe it didn't disrupt the binary, or maybe it did, but then another one came by because you had so many stars in the center of the globular cluster or something. But yeah, that's for the theorists to figure out that one, especially stars that are black holes that are this heavy.
Okay, thank you.
If from the perspective of, say, someone standing on Earth a billion light years away, time appears to slow down for these at the event horizon of these black holes, how come, from the perspective of the Earth, their rotation around each other also doesn't slow down, since from our perspective, time is slowing down for these objects?
Well, it's still slowed down by the same amount, so you couldn't, just because they got closer doesn't mean it would slow down by more.
Right?
I
don't understand.
So, I mean, we look at the thing. I mean, that whole thing about time slowing down, that's just one observer watching another observer falling into the black hole.
All right, now
so
you're watching one black hole fall into a black hole.
Watching one black hole fall into the other black hole. Well, they were both already really close to each other. They already warped space and time a lot where they were. So it isn't that much different once they merge than looking at the two of them separately.
Okay.
My question was about the applications of, now that we know that gravity waves exist, is there any application of that? And secondly, can we do something that produces gravity waves on demand?
Okay, are there any applications of gravitational waves? No. Not likely to be any for quite a while because it's such a tiny effect that it took so long just to even find out that it was happening. And what was the second question again?
Can we somehow produce them on demand?
Oh, can we produce any gravitational waves on Earth? Not anything that we have the ability to detect right now, because these are incredibly massive bodies and they still made this incredibly weak signal. And so there's no, I mean, Earth itself is nowhere near heavy enough to do anything, even though it's an oblate spheroid. So, I mean, everything is making gravitational waves because the Earth is not a perfect sphere and it's spinning around, but we will never be able to detect those. Those are so much weaker. And, you know, this is basically at the edge of our technology right now.
Thank you.
How does mass become gravitational waves, and why do gravitational waves travel at the speed of light?
Okay, gravitational waves travel at the speed of light because that is part of the theory of general relativity, and it's actually a prediction when you go through all of Einstein's equations, which are is not going to happen tonight. They're tensor equations. It's a system of 10 coupled partial differential equations, and if you work through all of that math, you can actually find where the waves travel at the speed of light when you get to the end. And I direct you to my website here where I have these course materials. If you want to work through all that math, it's in the section called Geometry and Gravity of Weak Fields. It's about the simplest explanation we could come up with to explain Einstein's equations to teachers that don't know the math that you need to know to understand the general theory of relativity. So it's still very, very hairy, and it's about a 45-page chapter of really, really complicated math. But if you work through all of that at the end, you will see where the speed of light comes out. And then what was the first part of the question?
How does mass become...
Oh, how does mass become gravity or light or something, or waves? Okay, so as I said before, each black hole is curving space-time around it. And when the two black holes merge, the final black hole curves space-time around it. But the curvature is different for the one black hole versus the other two black holes that you started with. So that excess curvature turns into energy that travels out at the speed of light. And those are the waves that we see. It's all part of E equals mc squared if you want an easy version of Einstein's equations. Right? That's the equivalent between energy and mass.
We'll just do the people who are standing now.
Okay. Yes, sir.
There's directions associated with the dilations and contractions that the waves produce, and there's directions associated with the arms of the detectors. And so if those, the orientations of those directions can be different depending on what direction the wave comes from. So is the detector equally sensitive regardless of the incoming wave, the direction of the wave?
Yeah, the waves go right through the Earth, so it doesn't matter really what direction they came from. But because the waves have this quadrupole type geometry where when you stretch one axis, the other axis shrinks, you're going to get, the two arms are always going to be, and since the two arms are also at cross, at right angles, whatever one arm does, the other arm will do the opposite, no matter what direction it comes from.
So the answer is no then. Doesn't matter.
No, it doesn't matter.
Okay.
And we have one more over here.
You measured the changes in space. Could you also measure the changes in time?
We measure the changes in space-time, right? Because in Einstein's theories, space and time are mixed up. So we are all traveling through space-time at the speed of light right now. And you might say, well, how could that be? We're all sitting perfectly still. Yes, or at least you are. Yes, but while you're sitting still, you are aging 1 second per second. So you are traveling through time at the speed of light. You're just not traveling through space. When you start to travel through space faster and faster, you travel through time slower and slower. So think about that the next time you're wondering about space and time. And that was something that Einstein figured out, right? That space and time get all mixed up. And last question.
I have two questions, one very simple and one, well, kind of obnoxious. The simple one is, I don't believe that you indicated how far away the smaller of the two binaries was. Okay. 1.8 parsecs, light years away was the first one, and the second one was how far?
No, they were both about 1.3 billion light years away, so about 400 megaparsecs.
Thank you.
And multiply by 3.
And my kind of obnoxious one was that I accept your results, but ever since I was aware of LIGO, I've had kind of a issue with accepting the fundamental theory of how such a thing is presumably observable. It should not be because we are stressing or talking about the Einsteinian issue of the stretching and squeezing of space, which we all know are just models of speech. If a vastly greater event, say in a thought experiment, had happened, what would we observe? Absolutely nothing, because space itself is contracting. How is a machine presumed actually to come up with a number?
Okay, space itself is not actually contracting. Actually, the universe is expanding, but I'm not sure that's what you were really asking. So
in the fabric of space-time itself, we existing in the system of that space-time, how is actually an observation of your machine actually coming out with a distance of contraction and expansion, however small, insofar as that in my well, the concept of it.
Yeah, I mean, the distance that we're measuring for the change in the length of the arm, right? That's actually a precise number. That's what
I accept your observations.
Okay, I think we're now at philosophy rather than physics and astronomy. So this may be a good point to end. And let's thank Dr. Kaminsky again.